First speaker is Jackson Dagger. He's from the University of British Columbia. He's in his 5th year of undergraduate studies. And he focuses on analyzing real-world applications for in-memory processing, and is broadly interested in OS and security. So not this summer, but next summer you might be interested in an internship, so keep track of him. He'll present both JPEG encoding on in-memory processing. It's a short paper. Go ahead, Jason.
Hi, my name is Jackson Dagger. I'm an undergraduate student at the University of British Columbia. I'm here to present our paper, Bulk JPEG Decoding on In-Memory Processors. This was co-authored along with Joel Nider, Nilu Gravi, Daniel Ng, and Sasha Fedorova. So fundamentally what this paper is about, as hopefully you can glean from the title, is we adapted JPEG coding to a real-world processing and memory system, specifically that by a company called UpMem. Through that, we were able to better explore the strengths and limitations of UpMem's architecture, and as well, we were able to take a look at how PIM performed on compute-bound workloads. And so hopefully you're all familiar with JPEGs, because if not, I'm not explaining to you what an image is. It's a lossy image compression algorithm, meaning you're going to lose some information when you put your image there. I'm sure we've all, uploaded an image to Facebook and it's come out and everything's kind of a little garbled. And in the age of the smartphone, we are seeing billions of images produced each day, many as JPEGs. Companies like Facebook, Twitter, and Instagram all have massive image repositories, and their users are uploading millions or even billions of images each day. And gone are the days where these companies are responsible for getting an image, for storing an image and distributing it to someone's followers. Now they have a great deal of machine learning tasks like mining and tagging to perform on images that are coming through their data centers. One very cute example is Google's ImageN. You probably saw this recently. It's a text-to-image model by Google. Behind this incredibly cute cat playing a guitar, maybe we can train one of the outdoor cats to do that, but it might be a little hard, was a repository of 400 million images that had to be each decompressed to be fed through this model. So obviously, as deep learning researchers' appetite for images to process grows, so will these workloads that systems researchers have to adapt to. So as you can imagine, there's been a great deal of research into accelerating JPEG decoding on hardware. For example, the current reference implementation, libjpeg turbo, achieved a 4 to 6 times speed up over the original libjpeg using SIMD instructions. NVIDIA has also come up with NVJPEG, which uses their GPUs to accelerate JPEG decoding, and we've also seen ASIC and FPGA work. But until now, we haven't seen this adapted to processing and memory. So let's talk a little more about what processing and memory is, or PIM. So PIM was originally created as a way to get past the memory wall. In recent years, compute power has raced ahead of the capabilities of memory. And like a Lamborghini stuck in traffic, the modern day processor waiting on memory accesses is wasting its hardware's capability and it's wasting energy. One solution to that is to bring your processing power closer to your memory, processing in or near memory. While this has been subject to a great deal of simulation and theoretical work spanning decades, we're only seeing real processing and memory systems on the market in the past few years. One example is Samsung's function in memory, which is an AI-specific accelerator. However, what we're working with is from a company called UpMem, which released a general-purpose, off-the-shelf DIMM, PIM-accelerated DIMM. So let's take a deeper look at what we're actually working with. So for every 64 megabytes of DRAM, UpMem has embedded a DRAM processing unit, a DPU. This DPU doesn't run directly off the DRAM, but rather off a 64 kilobyte scratch pad bank. All information has to be copied between the scratch pad and the DRAM manually by a DMA. And finally, when we take a look at our core, we see that it's quite lightweight. So for example, it only runs at 267 megahertz, or at least the one we used during testing did. It doesn't have floating point support, or many of the other hardware bells and whistles you'd expect from a general purpose CPU. It runs with up to 24 hardware support threads known as tasklets, and we'll go into a little bit about the advantages of those later. And I think it's important to note that this is a very new technology. So for example, we researched with this 267 megahertz version, but right now on the market, they're now up to 400, looking at 500 and 600. So, when we're dealing with a technology that's so new, we're able to see, that growth because PIM is very much learning to walk still. And so there has been some previous research on PIM and specifically UpMem's architecture. One key finding has been that you're often wasting compute power if you're not using 11 or more tasklets. This is because their pipeline has 10 serial stages plus 3 parallelizable ones at the end. And so essentially you're not going to be retiring at least one instruction per cycle unless you have 11 or more tasklets running. We've also seen that there's no native support for inter-DPU communication, which means that the applications that require DPUs to talk to each other have to go to the CPU. And you end up with the reverse of the problem that PIM is supposed to solve. You have your memory waiting on your CPU, which is, no good. We've also seen that it's often insufficient for compute-bound workloads, and that's especially true when you have specialized hardware. So for example, we ran AES encryption on PIM, and when we compared it to like an Intel CPU that has their special instructions for that, PIM was just blown out of the water. And so this architecture provides a few challenges specifically when we're talking about JPEG decoding. First of all, we have to figure out a way to split up the work between many tasklets if we want to optimize that compute power. We only have control of the DPUs in ranks of 64, and we don't have that inter-DPU communication. We also have that tiny scratch pad, and I think not many of us are used to, carefully managing 64 kilobytes of memory. And in fact, that limited us to the stacks of 15 tasklets. And finally, for one important part of the JPEG decoding algorithm, which I'll go a little more into, we didn't have floating point support, which was originally a necessary part of that algorithm. So before we go further, I really need you to remember 3 things about how JPEGs work. So the image is broken down into these 8x8 pixel blocks called MCUs, minimum coding units. The MCUs can mostly be operated on independently, compressed and decompressed, mostly independently. We'll get a little into that soon. And the discrete cosine transform and the quantization are what are doing the heavy lifting of the compression and are taking up a lot of the compute time with decompression. And so let's take a deeper look into the 4 steps of decoding JPEGs. So we're starting assuming you've already taken your MCU's minimum coding units, and each MCU is Huffman decoded. It's important to remember since these MCUs are compressed individually, they're going to be of variable length. So we don't know, if we just pick a random spot in the middle file, we don't know when one MCU will start. Next, we go to the dequantization phase, which is simple multiplications, essentially mapping the MCU, which is that discrete quanta, just multiplying values back in. We then do the inverse discrete cosine transform, because at this point we have a matrix of frequencies, and we have to map them back to pixels. And so that's that floating point operation I talked about before. And then finally, we need to map back to the familiar red, green, blue RGB color space, because if you don't know, JPEG uses a different color space for reasons that I don't have time to get into. And so, and that's just a little more multiplication. So with all these challenges, why should we use PIM to accelerate JPEG decoding? So first of all, one of those fundamental limitations of PIM we talked about is no communication between DPUs. Well, if we do what our team did and have each image on a single DPU, you don't need communication between DPUs, since obviously how you decode one image has no effect whatsoever on how you decode another image. We also saw that multiple tasklets are needed to effectively harness that compute power of the DPU. Well, that lines up with how the MCUs work. We can divide the work of JPEG decoding by MCUs. So once again, we see that lining up. And finally, one of PIM's superpowers is that it scales with the load in memory. And that lines up, again, very well with how JPEGs work, with the decoding load scaling with the memory load. And so now I'm going to talk a little bit about the design choices we made. So first,
decoding 2 images of the same size will take the same time? in JPEG? So you got, let's for example, you have two images, two JPEGs that you need to decode. Will decoding both of them?
Not necessarily.
At the same time?
No. So that's one challenge I'll talk a little bit more about, but essentially, as I mentioned before, we do have that issue when we have rank control of the DPUs. So essentially, the 64 DPUs are going to be waiting on the slowest image to decode, and so that was one of the limitations we ran into. Fundamentally, it ends up that it just makes sense to try and batch images approximately by size. And so when we load an image onto the DPU, first we're parsing the metadata, and so it's essentially the tables we need for the next part. And then here, as I mentioned, it's Huffman decoding. So what we want to do is we want to split the MCUs by tasklet. However, we don't know in advance where one MCU will start and one MCU will end. There's a really cool feature in the JPEG format where they specify restart markers, so you know where one MCU starts. And I'm sure we've all ran into something like this before. It's a really cool feature. It'd be really helpful. And on the images in the wild, it's nowhere. So we're just kind of, it's cool to think about. We can't actually use it on most images. So instead, we have to do something a little more fun. So as you can see here, this is obviously 16 MCUs, is not a lot. But so let's say we're splitting it between 4 tasklets. As you can see, if we're splitting it evenly, some of these tasklets are starting in the middle of an MCU. This is actually okay. There's a really cool feature of Huffman decoding where as the decoder discards incorrect codes, it will eventually self-synchronize. However, we don't have an upper bound on when that self-synchronization will happen, which is a bit of a scary position to be in. So every tasklet has to check the work of the tasklet in front of it to make sure it started decoding MCUs correctly. So let's say tasklet A will go into tasklet B's MCUs until it sees that it's decoded 3 correctly and it knows it's on the right track. And through that, we're able to split it up and have these tasklets each, most of them perhaps starting incorrectly, but eventually getting on the right track. Next, we move to the dequantization phase. This is pretty quick and simple. It's essentially just, we have an 8x8 matrix and each value is multiplied by once by a different value from a quantization matrix. In that dequantized matrix, we then have to adjust some coefficients. Essentially, the coefficients on the MCUs are adjusted in serially when encoding the JPEG, and so they have to be adjusted in serial when decoding it. Unfortunately, this is one of those things where you're just left with an area that just can't be parallelized. This is a completely sequential operation, so that just takes place on one tasklet. Next, we move to the inverse discrete cosine transform. So as I mentioned, we're mapping from cosine frequencies coefficients back to actual pixel values. And that, what we do is we approximate those floating point operations with integer multiplication. And I will talk a little more about why we are confident that it's fine to do that in a second. And then finally, we bring ourselves back to the red, green, blue RGB color space you're all hopefully familiar with. So PIM is a very different architecture from what we've seen on, say, CPUs. So we obviously had to take a trip pretty far away from the reference implementation. So we have to make sure that we are still decoding images correctly, right? And so we know with the little adjustments we made, the difference between 64 and 32-bit and no floating point, we're going to see some difference. But JPEG is a lossy compression algorithm, and it's okay if you lose some information fundamentally. So here you see the peak signal to noise ratio, where we took as our reference images decoded on the CPU, and as our distorted and compared them with images decoded on the DPUs. Now 32 decibels, previous research has shown, is the threshold for human perceptibility. That means that in that region, all that region to the right of that line, you would not be able to tell the difference of the images the images decoded with the reference and images decoded on the DPU. And so you see very small within, this is going to be barely perceptible differences here to the left of the line because they're so close. I could show you a visual of 2 images that look exactly the same or near exactly the same, but that might not make for an incredibly interesting presentation, I think. Next, we look at the structural similarity index, which is a similar method of comparison, but this time it's They use a little more, well, really cool statistics. I can't go into it right now, but to try and better recreate how humans see natural scenes and how they see the distortions in them. And so one is what happens if you put two exactly similar images together. And you can see we have like our peak very close to 1. And so this indicates that, again, as humans will see it, we're not going to see a lot of distortion. And now that's all good, but now we need to consider, most of these batch JPEG decoding is going to be, not seen by a human. It's going to be going through various machines, machine learning. So how will machines see the distortions in our image? And so what we did is we trained ResNet 18. It's a fairly popular neural net architecture on TinyImageNet 200. And so the accuracies we saw were broadly similar. So we trained the model once on images decoded on the DPU and once on images decoded on the CPU. We then evaluate it on an evaluation set decoded on the DPU and an evaluation set decoded on the CPU. When we see the comparison between accuracies, the model trained on images decoded on the DPU does slightly better, but it doesn't appear to be statistically significant. However, we can be confident that we can be fairly confident that machine learning tasks will not be hindered by our implementation compared to the reference implementation. And so, performance. As I mentioned, DPUs are very lightweight processors. So when we put one of them head-to-head with a single Xeon 4110 core, it gets blown out of the water. That's to be expected. However, we see that beautiful scalability of DPUs as we scale up, we quickly see it able to match a core for a very lightweight, cheap, and energy-efficient processing setup. We also saw another interesting thing is that when we incorrectly decode those MCUs, as I mentioned, to synchronize between the threads, that's actually not particularly helpful if you have a small image, because you don't have as many MCUs, so you end up doing the work 2 or even 3 times. And so, that's something we see across a lot of computing domains is, synchronization, parallelization could be nice, but if you spend a bunch of time, syncing your threads up, it can actually end up syncing you a bit. And then finally, here's an actual breakdown of what the DPUs are doing. And so you can see, first of all, the DPU initialization library right now is not very optimized. So we have that kind of big, ugly 10% at the start. And then you can see it's really all these lots of multiplication on the DPUs, since those 3 big blocks, those are all the dequantization, the inverse discrete coding, inverse discrete cosine, and the color conversion. And since DPUs, you have to emulate that multiplication. They don't have a native multiplication unit. And then we can look again, we see that wonderful scalability of DPUs in play, where as you add more and more images, you can really get these massive throughputs to enable these large data center operations. And you can also see, and again, as I talked about, those DPUs do have that annoying initialization time. And so once again, you can see that second little bump, where if you're able to spread that initialization time over multiple runs, it can be very helpful. So what can we take away from all this? We can see that PIM can effectively accelerate JPEG decoding when there's a sufficient amount of images. This is key because we found JPEG decoding to be a rather compute-bound task, and so to see PIM's scalability enable it to help with not just memory-bound tasks, but compute-bound tasks is big. We also saw that PIM, this confirms a lot of previous research that PIM is especially helpful when high throughput is needed and high latency is okay. As I mentioned, that we saw that you needed 200 cores, 200 DPUs to emulate one Xeon core. You're still going to, the latency is still going to be 200 times worse when you're running those 200 cores. And then finally, we saw another little fun thing is when you're doing lossy compression decoding with JPEG, and potentially with other compression algorithms, you might not need to actually use that very expensive floating point hardware. Thank you.
So while you warm up with your questions, I have a couple of questions. You described various limitations that you had to deal with. Would you say that they are or are they specific to the Upman GPU that you work with?
Yeah, I think I guess the two big limitations are that we don't have, I mean, the processors are very lightweight, and that we don't have much effective communication between the processors. And so there is a way to have more communication between the processors, and that's a very expensive on hardware muxing architecture, as well as an added level of complexity for the programmer. And then, of course, you can make the cores more powerful, but that's going to be more expensive in both material and money. So there's nothing necessarily stopping someone from trying it, but it's just making a bunch of very expensive cores is inherently expensive.
There is a PIM in which you actually use the cells, the memory cells, to compute, usually using resistive memories. Have you thought whether such a thing, obviously it's very simple, you want to do simply-like logic operations in cells, so it's very slow, but millions of parallel things. Have you thought whether such a thing would be better on these things?
Yeah,
Could you repeat the question?
Yeah, I said that. Oh, okay.
Or yeah, so essentially PIM this kind of this taxonomy, and so what we're actually doing is processing near memory, and there's actual processing in memory where it's directly on the memory cells. And he was asking, have you thought about would that do better? And I think my first, I haven't really thought about this before, but my first instinct is to say no, since this was already kind of pushing out a little, trying to get PIM to do a more compute-bound application. And so I think something like that, the real in-memory computing, I think might struggle to make that. But, yeah.
What is the exception model for this high parallel computation? So what happens, for example, for the JPEG decoding if the images are corrupt, or if some of the calculation fails? What is happening then in the machine?
I mean, yeah, so right now this is just an academic experiment, so it just right now just prints out and it'll just say either the DPUs are in fault, or it will say it will just wholesale reject it if you try and give it an image that's too large, because so far we haven't split images across DPUs.
In the flow diagram that you presented, there was one block that you were unable to parallelize, right? So can you elaborate on that? And is that the real bottleneck?
Yeah. So I think that was the bottleneck. A little bit of one. I think it was very. I don't have the exact math off the top of my head, but essentially each you have your matrix, and the top left coefficient in that matrix is adjusted based on the ones in the previous versions, and so it's very quick just going through the matrices. But it's but there's no, since it depends on the calculated version of the previous one, there's no way to split it at all.
Okay. Should you want to get prepared with CPU, what would you need other than what the engine is building up? The floating point operations, or is there performance decision you have to make to get this prepared?
Parity as far as
I want to get the same image as the CPU.
Yeah, I think going through, I think it should be most of the other thing is it's a 32-bit versus 64-bit processor. So so you would have to be, I think, getting a 64-bit processor with a floating point engine. Yeah.
So you're missing some operations other than floating point?
I don't think so, but I guess it's just more when we were approximating the floating point with integers, we stuck to 32-bit integers. So when there's versions on the CPU that also approximate the floating point, they're more precise.
Oh.
Yeah, last one.
You said that MCUs are mostly independent when they're not. How do you evaluate the diffuse don't intercommunicate?
Pardon me?
You said that MCUs are mostly independent. How do you handle it when they're not independent and diffuse don't really interconnect?
Oh yeah, so that was my the point about like we had that part in the middle that's in serial, and so right now we don't have images split across multiple DPUs. That's in theory possible, but it would involve going back through the CPU to get that adjustment and that part done. So yeah.
So, 10 more seconds. I was promised 10
Very
seconds.
quick one. The ratio of 64 megabytes per DPU, do you find it to be good, or do you think they should go to more or less from your experience?
Well, that's a tough one. I would say it's definitely been limiting before. I think I don't want to ask because like I mean I know I'm sure the people designing this hardware are banging their heads on the table trying to get this all working, but it would be kind of nice I think if you could have like scalable, like if you had maybe you have like your like 128 meg model as well, and then maybe that has and change the ratios, but that's not something they have right now. But, yeah.
Thank you very much.